Hi. Good morning, everyone. Thanks for coming. I've been an NDC fan for quite a while, first-time speaker, so I'm a bit anxious and excited, so go easy on me. We'll be talking about containerized applications now, and we'll be talking about how to properly design and structure your containerized application in such a way that you won't lose data. Now, data and storage is an issue when it comes down to containerized applications, and it's something that you need to consider when you're moving your architecture from those big servers that you used to run and move them over to containers. We'll discuss what containers are, give us a good basis for our discussions. We'll talk about build containerized applications, and then we'll move on to storage options and see what kinds of solutions we have when we want to run our containers applications. We'll finish up our talk with a use case. We'll actually take a real live use case and see how we build the solutions to keep it running even though it's still in a container. Talking points, basic introduction, who am I, what it is that I do. We'll give some introduction to containers 101. We'll dive into some theory of what containers actually are, how they work, how they function, how we can build them, how we can put files or manipulate them or run them. We'll look at how some of the challenges of running a distributed system, break down small containers, lots of containers, what are some of the challenges that we might encounter. We'll move on to storage, picking the storage solutions. We'll take a look at several solutions. We'll look at examples of when and how to use the proper solution for each case. We'll take a look at the use case, and then we'll summarize and have some questions. All right, so let's get started. This is me. My name is Hagai Barel. I'm a senior DevOps consultant at a company called Code Value. We're an Israeli-based company. I'll talk about in the next slide. I've been doing a lot of containerized work in the past year and a half. A couple of systems running in production, some on staging, some on testing, all kinds of interesting use cases of containers as part of the application lifecycle. I do a lot of designing, infrastructure design, to support those containerized applications. Some are on-premise systems running in the local data center. Some are cloud deployments, Azure, AWS. Other than that, I do talks, I teach, and I train. So that's basically me. Code Value, we're an Israeli-based services company. We do professional services in the software world, everything from UI, UX, software design, agile mentoring and process implementations, DevOps, you name it. And we also have an extension called Ozcode, which is a Visual Studio extension for C# debugging, with a ton of cool features, link debugging, heads-up display, all kinds of interesting stuff. We have a booth in the entrance to the floor. Go check it out. Really cool features, a lot of great stuff. All right, so that's basically me and us. So let's talk about containerized application. Those aren't containerized, okay? That's the way we used to build software, okay? Now, this is a pretty common setup for, just any software system. You have your 3 layers, your 3-tier setup. You have your presentation layer, you have your business layer, and you have your data layer. The presentation layer, it's pretty common, it's pretty standard. There's nothing unique about that. Your presentation layer is the interface, the graphical interface that your user interacts with the system. All your heavy lifting, all your logic, all your code, data manipulation happens in the business layer. And the data store actually stores that data long term. Now, the problem with such a setup, or one of the problems with the old school, big, fat, monolithic setups, is it's really hard to build these things. Not writing the code, but actually building it, compiling the solution. The solution can have hundreds of projects. If you want to change one line of code, you have to build that solution from scratch, basically. You got coupling inside your project. they reference one another, or they reference other projects and other solutions. You got a big giant mess of components that you can't really easily reuse. If you want to introduce new features, if you want to fix bugs, you have to build that solution again and again, compile the whole system, and deploy it as one big unit to staging environment. It goes through a pretty long cycle of life cycle just to get your system up to production, fixing your code, or introducing a new feature. It's hard, okay? I can tell from experience, I've been working with clients that have these big monolithic applications. It's hard. It's really hard to build this huge system which has like hundreds of dependencies, NuGet packages, references, dependencies on databases. It's convoluted. It's a mess, okay? We've been doing it for a while. It's a mess. As a solution, okay, so let's not work in this big monolithic fat application. Let's try to break it down. And the solution is actually breaking it down to small components. Take each one of those huge layers and just break it up to simple components. Small components, atomic units. Each component does just one thing, okay? It has a high cohesion. It's very granular. It's very small. It's very atomic. And this also means that I can work on each component independently of the other system. No dependencies or very low dependencies between the components. And I can actually build a whole life cycle for each component. This isn't really a new concept in software design. This is the microservices concept. We've been doing it for a while. We haven't called it microservices. We called it service-oriented application, SOA, for a while. But microservices actually is an extreme SOA. It means take that service, break it down to very, very, very small components, build and develop each component on its own, independently from the rest of the system. Now, the problem with such a setup, microservice setup, it's hard to deploy it to production. Previously we had that presentation layer, it was one chunk, you build it, you took it, you deployed it to your environments. Now we have to deploy a lot of small atomic units. Each one has to be packaged, each one has to have its own dependencies, its binaries, its libraries. Each one has to be packaged independently from the rest of the system. Sorry. So what are containers then? And how do they help us build these applications, those distributed applications? Containers, and we'll discuss it in just a bit, are exactly that missing piece in the deployment cycle. They can help me actually package and isolate each microservices and deploy it independently from the rest of my system. All right, so that's the high level, the overview. Let's take a theoretical spin to what containers are. Those are containers, by the way. It's a shipping yard in England, I think, somewhere. All right. So, containers. Well, theoretically and very, very, very high level, looking into containers, containers are basically a method of an operating system level virtualization. Now, that's a fairly complex sentence. Let's break it down a bit. Think virtual machines, okay? A virtual machine is basically a computer. It's a virtual computer. There's no physical hardware that's associated with that virtual machine. It runs on a hypervisor. It's a software component that actually mitigates between my machine and the hardware requirements underneath it. It emulates those hardware resources for my machine, for my virtual machine. I got virtual CPU, I got virtual RAM, I got some disk storage, I got everything I need to run my virtual machine. Containers, on the other hand, are similar in that way that they're actually virtualized and isolated, but they don't require a hypervisor in order to run. We don't need to emulate a whole computer just to run a container instance. It's small, it's isolated, and it runs directly on the kernel. That means that it's really quick, and it gets its resources directly from the kernel. Now, containers actually allow us to run applications in resource-isolated processes. Very similar to virtual machines. These are isolated from the rest of the operating system. But unlike virtual machines that I have this huge computer, this huge machine, and multi-process, this is a single process, very small, that happens in the OS level, right? Now that isolation and encapsulation is achieved using two features called namespaces and control groups, which basically give us something like this, all right? This little box over here, that's a container, all right? That's a namespace, which is isolated from the rest of the processes in the system. Now, the processes running inside the namespace can affect processes outside of that namespace, meaning that the processes running inside the container can't affect or modify other processes in the system. The other processes can affect those inside the namespace, inside the container, but not the other way around. And that's the isolation and the encapsulation that we get by using a container. Okay? It's a single process, which has a subtree of itself, but that's basically it, right? So whenever you hear the word container, this is it. Okay? It's a small namespace that confines a subset of the process tree. Now, control groups is the counterpart of the namespace. Control groups actually allocate resources from the operating system to that namespace, meaning how much RAM does my namespace use, how much CPU, how much I/O, how much networking, how much storage. Okay, so there's two features that are counterpart. They actually complete one another. All right, so those are containers. But how do we build them? And how do we run them? So the containers actually are what is actually running. But in order to build one, we have to use an image, right? Now, an image, you can think of an image as a blueprint for running a container, okay? It holds all the relevant information that my container needs in order to run. You can think of it as the image is the design time construct, and the container is the actual runtime construct, okay? It's like a class and an instantiation of that class. It's basically just a file, okay? It's a compressed file, which has everything inside, all the code, all the dependencies, all the references that my code actually needs in order to run. Now, there's several ways to build an image. Using a text file is probably the most common. You write inside your text file, you declare what the things you need inside your image. It's basically just a set of instructions on how to build your image. Think of all the usual things you do when setting up a new server, okay? You go out and you install all the updates and security patches and stuff like that. Then you go out and install all the third-party dependencies you need. You need .NET Framework, you need whatever your code needs. And then finally, you put your code inside that server. Building an image, it's pretty much the same thing, okay? I start with this base something, okay? And then I put inside that my dependencies, my third parties, my bins, my libraries, and I just put my code inside of it. I package it in a file, and that's the base of all containers. Now, containers aren't mutually exclusive to an image, meaning I can run several containers from the same image, okay? Now, a key point to this image container thing is that images are immutable, meaning you can't change them once you build that file. You can build a new one, which is great, but you can't change the already built file, which means that if I have changes in my code, I'll just build a new image and put the updated code inside that one, okay? Sorry. All right, so to sum it up, what's the benefits of actually using containers? Well, the first and foremost, the main benefit of using containers, it's really, really fast, all right? Fast startup times, fast shutdown times. It takes about half a second to a second to get a running container once you have that image on your computer, okay? Just put in the command on the command interface, on your CLI, bam, you got a container, okay? Again, this is an OS level virtualization. You don't have to go through the hypervisor, okay? Just create the namespace, allocate the relevant C group, and you got your container. So they're really fast. They're easily scalable because they're really fast, meaning I can have like 5, 6, 7, 8 instances of that same container. And that image that we just discussed can contain just the stuff that my code needs, okay? I don't need the whole computer. I don't need the whole operating system that has things or baggage that I don't need, okay? I don't need 2.5 gigabytes of Windows Server just to run 5 DLLs. I don't need compatibility to printers or whatever. I can use just the stuff my code actually needs. My binaries, my dependencies, and my code. Okay? And again, the process isolation we discussed earlier, which means that if my container crashes or I need a new one, it doesn't affect the rest of the system. Okay? So these are main benefits of using containers, and that's actually what makes them so perfect in a microservice-based microservice-based design. They're small, they're atomic, they're granular, they boot up really fast, and they're really easy to scale and replace. But microservices and distributed systems have challenges, major challenges. And once we got our head wrapped around the concept of containers, let's move on to some of the challenges of running a distributed system. All right, so we got like a bunch of containers running. There's only like 3 servers we used to have in the old days where we knew exactly where each one of them is, what kind of operating system it runs, what its storage needs, how patches, the whatever. Okay, we got a bunch of containers running, which is great because we want it scalable, we want it small, we want it granular. But there are some new challenges that we need to consider. Now, these 3 challenges or issues are challenges of every system, okay? You can break down every system to basically the 3 main pillars of things that it needs to run. It needs compute, meaning it needs CPU, it needs RAM, the actual stuff that runs our code. It needs network to communicate with other components in that system or externally. And it needs storage. Now, storage is the main issue of our talk, and we'll further dive into it later, but let's briefly talk about compute and networking, okay? So, compute. Well, you got several issues you need to discuss or you need to attend to in the compute section. You have to make sure you have resources, enough resources that your code needs in order to run. And it means it has enough memory, it has enough CPU, and you have to allocate those resources to the components that actually use them. Now, one of the main tools you can do that is by using scaling, okay? Those of you unfamiliar with the scaling concept, it means how much dynamically allocation of resources I can do or how to do it to a single component. I can do it vertically, which means more RAM, more CPU to that instance, or I can do it horizontally, meaning more instances, okay? Think of it like a matrix that grows on the Y and X axis, okay? Vertically and horizontally, okay? More instances or more power to one instance. More instances means you need more machines, obviously, okay? You need more hosts so you can place all your instances on them. Vertical means I need a beefier instance, more resources to that instance. Now, scaling, horizontal scaling, that's an issue all by itself, and it's actually an even more complex problem than you might imagine, because once we go multiple instances, we need to start thinking about placement. Where do we place instances? We got like a bunch of hosts. Let's say we got, I don't know, 10 machines, 10 nodes running inside of our system, and we got like 1,000 containers. So we need to allocate those containers or place them on the hosts smartly or intelligently, or maybe just distribute them evenly. So it's an issue all by itself. It's container placement, okay, where do I put them once I got them. There are other issues like how to keep them alive, how to get their heartbeat. Is it alive? Is it dead? If it's dead, let's schedule a new one. Let's put a new one. How do I replace old containers with new one? How do I update the system? Do it rolling, do it blackouts. A lot of concerns around that. All right. Let's talk about network. Some of the challenges you might discover or might encounter when running a distributed system, you need some kind of mechanism for discovery, okay? Meaning you have all your components running in the system, and they need to find one another. They need to communicate with one another, okay? They might do it over REST calls. They might do it with UDP, TCP, whatever protocol, but they need to somehow find one another. It's like, okay, where are you? I'm there. Okay, here's my IP. Great. And when you're running a distributed system and you got a lot of containers, that becomes a real issue, okay? How does one component find the other one it needs? How do we keep that list of services relevant when containers are replaced, when they move between hosts, when they die, when they start up? So service discovery is an issue. Routing, again, not so much of service discovery, but how does data flow inside my system? How does my system communicate with external services or internally? Policies, firewalls, ports, stuff like that. All the issues revolve around security. Are we running HTTPS or not? Is my network secure? Are we running SSL certifications? What's the trust level between components inside my system? Load balancing, it's another challenge, which is even more of a challenge now that we're running in containers, because we got like 8 instances of that same container. How do we balance the load on that instances? Okay, how do we grow? Again, scale, and connect that load balancer to our scale, to our instances. There are other challenges revolving around network. These are just an example of stuff that we need to consider. The third pillar is storage. Every non-trivial application, in the end of it, has to keep data somewhere, okay? It could be user details, okay? Its name, password, ID, which you probably store in the database. It could be files, image files, PDF files, just static regular files. Whatever it is, at the end of it, you'll have to keep your data somewhere. And if you're keeping your data somewhere, you have to make it available to those instances that need that data, okay? Now, again, we're running a distributed system, we're running multiple hosts. That means that that data needs to be available from multiple places, okay? We'll discuss it a bit later. Durability, I want my data to be there when I need it, okay? I don't want it to get corrupted. I don't want it to get erased. I don't want it to get deleted. I want it to be there when I need it. And of course, scaling. As my system grows, my data stores and my storage needs also grow, which means I need to somehow think of a mechanism that can allow me to scale my data accordingly with the scale of my system. Again, other issues revolving around storage, but some of the challenges. All right, so let's talk options. Storage solutions or storage options. What kind of mechanisms do we have? Some of them are old school, okay? Some of them are solutions that we've been doing for a while that aren't new. Some of them are a bit different when we're talking about containerized applications. So the first solution, or maybe the most trivial and straightforward one, just put your files in the container, okay? It's cheap, quotes. You don't have to do really anything, just files that are stored inside that container's control group or namespace. It's really fast because, again, you don't have to go somewhere else to look for your data. It's there on your local disk. And there's no special configuration. You just, as you always did, just save your file to the file system and just read it from that file system. That's like the most trivial and the most simple storage solution. Now the cons of that issue is you can't share that data. Again, it's bound, it's inside that namespace, inside that control group, and no other containers can read or access that data unless explicitly allowed. And again, this has very low durability. Containers are very short-lived, okay? They can die, which means I have to schedule a new one. I have to start up a new container. They can get replaced, which means I now have to take down the old one and start up a new container. So the durability of using an in-container storage option is very low. When should you consider using in-container storage? Well, static files, okay? Static files are part of your image. You don't really have to keep them somewhere else. They're already inside the image. And once you boot up or start up a new container from that image, those static files will be there. So there's no special storage consideration that you have to take when using static files. Cache data, again, it's cache data. It's very disposable. Just, the next time a container start up, just build your cache and you're running. I don't have to keep it somewhere else. I don't need to save it or consider or design a whole solution around cache data. And another option is when you're running a clustered application, which means that my instances know how to find and share data between themselves. And then they don't really require an external or a storage option. A great example of using container-based storage is Elasticsearch. Okay, if you're not familiar with Elasticsearch is a database of sort or a storage mechanism that is especially designed and optimized to deal with textual data. Now, Elasticsearch comes by design in a clustered model, which means I can run multiple instances of that same Elasticsearch, and they know how to share data between themselves, which means that if one instance dies, the other have copies or replicas of that same data, and you're not losing anything. So even if I haven't designed a persistent storage for Elasticsearch and I'm just running it inside the containers, again, those containers can find one another. Service discovery, we discussed that earlier. And they know how to share data between themselves using indexes and replicas and all kinds of neat stuff. Okay? If you're not running a clustered application, nothing you can't afford to lose. Okay? And that's maybe the main point here. If you can't afford to lose it, don't put it in a container. Okay? Put it somewhere else. Where you can put it? Well, again, you got a couple of options. You can put it on the host. Okay? Those containers, they're running on somewhere. Okay? They're running on some kind of computer, on some kind of operating system. So you can just put those files on that computer, on that computer's file system. This is great because you can now share volumes or share files between containers that are running on the same host. Again, you don't have to do any special configuration about the sharing. You just make sure, okay, that folder or that mount point is a shared mount point, and all my containers can access that folder. It's really fast. Again, it's on the host level, same as the container-based storage. There's no network calls. There's no bandwidth overhead and stuff like that. It's on the local disk. You can just read right to that disk. Now, the cons here is that data is bound to the host life, okay? Which means that if your host machine dies because of maintenance, because of failure, because of whatever, that data is lost, okay? So again, it's a bit better than the durability that we got in the in-container solution, but again, it's bound to the host life, okay? Which means that if you want to move from, let's say, on-premise data center on to the cloud, you'll have to take or migrate that data with you, okay? It does require some additional configuration. It isn't that complex configuration, but it's a bit of an overhead when you're using it. When should you consider to use it? A really good example of using host-based solution is for logs, okay? Just write all your logs to a central point on that host and have a log harvester just look at that folder and ship it out to a centralized log. It's a great example of using shared storage on the host, or a sidecar setup, okay? Sidecar setup basically means I have two containers, okay? They are dependent on one another. One of them fetches data, the other of them reads that data, okay? Now, in order to keep that data available for both containers, I can use host storage, okay? So let's say I have an application that reads tweets from Twitter. Okay, one part of it is the actual API caller that pulls the tweets from Twitter, and the other component reads those tweets and displays them to the user in a list or whatever. Okay, so I can have two containers here, and one fetches the tweets, saves them on a shared host folder, and the container that displays them just reads from there and displays them. Okay, that's a sidecar setup, which is great if you have two components that actually use or need some kind of shared volume to read and write data to. Okay, you have a placement issue here, because again, when we discussed compute earlier, if you're running a multiple host cluster, okay, you have to make sure those two dependent containers end up on the same host machine, because they need to read and write from the same data store. Okay. A great example is Fluentd. Fluentd is a log harvester, very similar to, functionality speaking, very similar to Logstash, part of the Elk stack. Fluentd, we can run it in a container, again, and have them look at a shared folder that all containers write their logs to. It just picks up those logs from that shared volume, ship them out to Elasticsearch or whatever, and then you get your centralized logging in one place, and you don't need to interfere with the containers. You need to stand your hand inside a container and grab those logs. Just have those logs saved on the host, and Fluentd can read the files from the host and ship them out. All right. And the third option, or the third solution, is using an external storage. Okay. Again, this is the most, Bell-proven technique that we have. We've been doing it for a while now. Most of our applications use some kind of external storage. It can be S3, network file system, NetApp, you name it. Okay. We have a storage that's externally from our system that is accessible to all our environment, for all computers or hosts running in that system. We can share it on all hosts, not just one host. Everyone can access that data store. It's scalable. Okay, just putting a new disk, bam, you got new storage. Okay, if you're running on your cloud provider, that's even easier because you get scale out of the box. You don't need to configure or do anything special about it, and it's durable. Again, you can back up it. It's one centralized storage, just back it up. If you had some issues with it along the way, just restore the backup and you're done, okay? Cloud providers have that scalability and durability already built in. So it's a great solution when you're running on a cloud environment. Now the cons here, there's some additional configuration. Substantial, okay? You have to set up the external storage. You have to buy hardware if you're running on-premise. If not, you have to configure your cloud provider's storage options. You have to configure your hosts on the same network or some kind of mechanism that they can access that host. Latency, that can be an issue, okay? Again, you're not reading from the local disk. You're reading from place on the network. So you might encounter some latency or performance issues, okay? Read-write locks. If one instance writes to a file, can the other instance read from that file? Or if they both write to the same file at the same time, who has precedence? Who has a lock on that file? There's all concerns that needs to be handled when you're dealing with external shared storage. Now, whenever you have critical data, okay? When you have data that you can't afford to lose, and you need to store it and save it for a long-term period of time, put it externally, okay? It's not bound to a host life. It's not bound to a container life. It's an external. It has its own life cycle, its own management, its own maintenance cycles. It's a headache of all by itself, but it's there, long-term, and scalable and durable, okay? Tons of options for external storage. We mentioned S3. We mentioned NFS storage, Blob Store if you're running on Azure. Tons of external storage options. All right. let's look at a use case, okay? This was actually part of the work I did for a client. And the story goes something like that. He had a whole application, a web-based application that did some calculations on maps. Okay, you had like this giant map of your country. You drew a polygon inside that map, and it went out to the database. It retrieved data. It did some image manipulation. Did all kinds of crazy stuff. But in order to run that those maps and those queries and polygons, they needed some kind of a GIS engine, Geographical Information System. Okay, and they decided to use Gale Server. Okay, but they wanted to do it inside a container, and Gale Server, by design, is a stateful application. It needs to save its maps, its data store somewhere. And we had to design a whole solution how to run Gale Server inside a container. So that's Gale Server. It's an open source. You can find it online. It's a Java application. It runs on top of a Tomcat web server, the application itself. Okay, and the server behind is the Java server underneath. And does all the heavy lifting of the data manipulation and retrieval, storage, and stuff like that. And the client is just a thin REST API call client. And those calls are processed by the server. Map data, files, stuff like that are all saved and stored in a file system, okay? Some kind of file system. It can be local, it can be remote, but those stores actually reside in a file system. So the solution was actually a two-part solution. The first part was actually building that Gale Server client, that instance inside a container. Okay, we based that on top of the official Tomcat image, and we just went out and grabbed the static files of Gale Server and placed them inside the image. What you see below is an actual extract from the text file, the Docker file we used to build that image. Again, it's just a set of instructions on how to build that image. And the run instructions, that wget thing, actually goes out to the internet, pulls down Gale Server's files that are zipped, and then it extracts them inside that image. So those are the static files. Okay, again, the Gale Server client that handles those REST API calls. The other part was actually designing the data store. Okay. We based it on an NFS network file system share. This was on-premise system. It wasn't a cloud-based system. So we had an NFS externally to the system. We basically just said, okay, this is the Gale Server folder. And we mounted that share to the hosts on all the data center so they can access that share. That was the actual Docker command we used to run it. Okay. The -d flag means it's detached, so this background process. And the -v flag, that's the actual interesting part, that's the volume mounts, okay? Which means we have a mount, a folder called NFS share Gale Server data that is mounted into the container storage of Gale Server. And that host mount was actually an NFS mount, okay? So we had the container mounted the host folder, which mounted an NFS share. That's a great setup because, again, if Gale Server dies, crashes for some reason, and another one is being booted up to replace it, it can access that same data store that is shared around all instances of Gale Server. All right. So that summarizes things up. Okay. Containers are short-lived, okay? By design, they're short-lived, okay? It's not some bug or flaw in the system, the concept. By design, they're short-lived, which is great because, again, when we're running a distributed applications and we just want to fix one line of code, we just start up, build a new image, start up a new container, and there you go, okay? Never put critical data inside your containers, okay? Because they're short-lived, okay? Put things that you can't afford to lose. Cache data, static files, stuff like that, okay? Hosts, they fail, okay? They go down for maintenance, they crash, they fail, they die, they burn up in flames, okay? Don't put stuff there too. Again, not stuff that you actually care about, that you actually want to keep long term. Okay? If possible, use cloud-provided storage solutions. They're scalable, they're durable. All the maintenance headache, that's not your problem anymore. It's your cloud provider problem. Okay? But performance is an issue. Okay? When you're using external storage, you must consider that performance, test it, see that it meets your expectations and your criteria when you decide between those storage options. And always remember, when you're running a distributed system, you need to distribute your storage as well. Okay? It has to be accessible, it has to be available, it has to be durable. Well, that's it. Questions, if you have any. Wow, you're a great audience.
You said Docker container runs on one CPU. Is that?
No, it's the Docker containers get their resource allocations from the host. You can use one CPU, you can use two, you can use 5.
So inside Docker, you can still utilize more CPUs.
Yeah. You can grow it vertically, okay, up to the resources you have in your system. Okay. Please.
I read an article that said, first of all, thank you, it was a great talk. I read an article that said that for volumes, like share a volume between containers and you put your data in the data volume, and then you can like destroy the container and then start other containers, reconnect to the same data volume.
Mm-hmm.
But they said that the challenge with that is orphaned data containers can sometimes be deleted by mistake.
Yep.
Do you have some kind of advice around that?
Don't put it in data volumes.
Okay.
Data volumes are great. Data volumes is actually it's a great concept around containers. It basically means I can have a container, a data container, okay, and other containers can mount or share that data container, okay. It's kind of like host-based storage, but in containers, okay. That files and storage inside the container, and then all the other instances just look at that containers and share it, okay. Now, what happens if that data container dies? Well, your data isn't really lost, okay? It's saved in the local file system. So when you boot up a new container, it can access that same data volume. Two issues around this. A, it's not really scalable, okay? When you're running on multiple hosts, you need to make sure that that data container is available in all kinds of hosts, which can cause some pretty overhead and performance issues. That's one thing. And the other thing, you might have some orphaned data volumes around, from deleted or obsolete data containers. It's a great options for mocking, okay? When you need to, mock a data store and you don't want to set up a whole new server or, put some additional software on your computer. Mocking is a great option, a great use case for using a data container. Just build a new image, a new container, put your mock data inside the container, and every time you need to write API calls or fetch that data, you can just start up a container that has that data inside. It isn't really scalable and it isn't really durable. So not really production grade. Right. Yeah.
So for databases, then you would use the host storage and be sure to run on the same host with this container, or is it more to it?
Database, well, Gale Server is kind of a database, okay? That's why it's a great use case. Keep your file. Even a database, even an SQL Server database, in the end of it, it has files it has to keep somewhere. It has LDF or MDF files or whatever, okay? And you can keep those files on external storage, okay? Which means they're safe. Okay. Again, this is critical data. It's crucial data. I wouldn't bound it. I wouldn't put it on a host. I'd probably put it on an external storage.
Can you? I guess that's another discussion. But can you actually run, let's say, SQL Server's files?
Yeah. You can.
On a share.
You can.
And it's performance.
Performance can be a flaky thing. You need to test it. But again, if it's not critical data, if you don't, it's not real-time data, okay? Your SQL query, okay, if it gets like a half a second delay, it's fine, it's okay. It isn't crucial time-based data. then it's great. Okay, put it outside, and you're good. If it's critical data, this needs some additional considerations. Time critical data.
What's the best container operating system?
They're all great.
But which one's the best one?
Not Windows. Ubuntu Server is highly tested. Okay, most new Docker container features are mostly tested on Ubuntu Server. I have a great experience with CentOS 7. Red Hat has some issues with running Docker, very, 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 very niche use cases, stuff like that. But most modern Linux systems with 4.0 kernels and above can run containers pretty much great. Not Windows.
What about the
Sorry, .NET guys, not Windows.
What about the system inside the Docker container? Because that can be a different operating system.
That can be whatever you want. You don't really even need an operating system inside the container. Operating system is a very convenient base for a container image, because by default, operating system have a lot of what my codes really need. It has network interfaces, it has environment variables, it has a bunch of stuff that my code usually needs. So usually we base our images on top of an operating system. I say, okay, let's take Ubuntu, for example, and then put my dependencies on top of that Ubuntu, and then put my code on top of those dependencies. And you get an image that already has an operating system inside. It isn't a requirement. You can do it without the operating system, okay? I've seen projects that are basically just compiled binary inside a container. It's a binary in a box, okay? And that binary has everything it needs to run, okay? Proxying, HTTPing, whatever, okay? It's a binary in a box. Again, containers are more of a packaging mechanism and distribution mechanism than an actual environment to run the code. You don't really need an operating system inside one. The bounds get really, really, really hazy. I've been doing it on my personal computer. Okay, I have a Windows 10, which has Docker on a virtual machine.
Windows Server on production.
It works. It should work fine. Okay, as long as containers are agnostic to the operating system. Okay, they're agnostic to the host. Okay, the same way that virtual machines are agnostic to the hardware. Okay, you got a hypervisor that actually does the resource allocation between the virtual machine and the physical hardware. Containers are agnostic to the operating system. Okay, they don't really care if it's Linux, what kind of flavor of Linux, or whatever, and they don't even care if it's a virtual physical machine.
I know, but is it?
It's visible, it's viable, if it's scalable, it is. Yeah, it should run great. It's a bit convoluted, but great. A better solution would be running ESX, which is a VMware solution on top of your hardware, and then your virtual machines you just drop Windows. You don't really need it as a mediator. Well, great guys, you've been a great audience. Thank you very much, and keep your data safe.